Welcome to our first video. Here's a worksheet that I didn't get to give you in class with some examples. There's about 11 examples and we'll try them here. I'll skip around and I probably won't get to do all of them. Let's start with example 1. The limit as x approaches -1. The first thing to do always is to plug in the -1 for x. And when you do that, you can see right away that it'll turn into 0 divided by 0, making it a removable discontinuity. So we're going to have to simplify that fraction, and hopefully it becomes something else that we can plug in the -1 to. So I'll rewrite the limit as x approaches -1 of x plus 1. And I'll factor out the difference of squares in the denominator. X plus 1, x minus 1. And then I can see that the x plus 1 terms will cancel out. That's how you remove the discontinuity. And so now we just have the limit as x approaches -1 of 1 over x minus 1. And that would just equal 1 over -1 minus 1, or -1/2. And there's our first answer. Let me now move on to example 6. The limit as x approaches 2 of the ratio. You can see for yourself that when you plug in that 2, you'll get 8 minus 8, which is 0. And 4 minus 4, another 0. So we get that special case of 0 divided by 0, which is a removable discontinuity. So we'll try and factor things out in this fraction. Here, however, notice that even though the denominator looks like a difference of squares, I'm not going to factor that out. I'm just going to leave it as x squared minus 4. It's still the limit as x approaches 2. And the only factoring I'm going to do is on top. I'll factor out an x and I'll have x squared minus 4. And now you can see that the top and bottom match exactly. So that's where my removable discontinuity is. And now I just have the limit as x approaches 2 of x. And I plug in my 2 into the x and I just get 2. So that's the answer to that. Notice then that by choosing carefully what to factor out, you can save yourself some time. I'm now going to try example 2 down here. The limit as x approaches 0 of quantity 2x over x squared plus 1. And once you see a few removable discontinuities, then you feel like everything is a removable discontinuity. But it's not necessarily the case. So what I'm going to do first here is just plug in the 0. And if I get a number on the number line, that's the answer to that problem. Notice that I'm not going to write the limit as x approaches 0 here because I've already plugged in the 0. So I am taking the limit now. 2 times 0, that's a 0. 0 squared 0 plus 1, 1. And against all popular belief, 0 divided by 1 is 0. And 0 happens to be a number on the number line. It's a good result. So my answer is 0. It is not 0 divided by 0, so I know it's not a removable discontinuity. It is a solid 0, and we'll keep it as the answer. Now I'll move on to something like example 7. Let's see what we can do with example 7. It's the limit of, as x approaches 1, of those two fractions there, or that one fraction with the two expressions. On the numerator we have a difference of squares, on the denominator we have a difference of cubes, and we talked about difference of cubes in class. So let's see if you remember how to factor this out. By the way, you should always feel free to pause the video and try the problem on your own, and then see how I work it out and see if we get the same results. That might be the best way to go about this. If I factor the numerator, I have x plus 1, x minus 1. I hope the color doesn't hurt your eyes there. And for the denominator, difference of cubes, this is how the formula goes. You ask yourself, what's being cubed first? X. What's being cubed second? 1. Because 1 cubed is 1. When you look at this here, what's being cubed? X. That's the x I wrote here. And what's being cubed here? 1. That's the 1 I wrote here. Because when you think about it, this 1 is the same as 1 cubed. And that's why I can say that 1 is being cubed. And the minus remains minus here. Now my second factor is going to be a bit longer, and all I have to do is square this term, x squared. That doesn't look like a square. Let's try that again, x squared. Then square the last term. When you square a negative 1, you'll get a positive 1. And then for the middle term, I'm going to change the sign from a minus to the opposite, plus. And then I'm going to multiply 1 by x. And that is just 1x, or x. And so that's what we have. And thankfully there's a removable discontinuity there. I can cancel out x minus 1. So now I just have x plus 1 over x squared plus x plus 1. And I can now plug in and when I plug in, I'll get 1 plus 1. And for the denominator, I'll have 1 squared, 1 plus 1 plus 1, so 2 over 3. And that's the answer to this question here. Okay, let me just take a quick look at the rest of the problems. And I'll encourage you to work on number 8. You can try that as a good exercise on your own. And here you're going to have to multiply by the conjugate of the numerator, which is 3 plus the square root of x. And so work on that, and then if you have questions on it, just talk to me in class. I will try number 9. Let's take a quick look at number 9. So it's the limit as x approaches 1 of this fraction, and because I have a radical, then I think I'm going to use the conjugate idea just like number 8. So this is what I'm going to try. I'm going to multiply by the cubed root of x plus 3, but now plus 2, which is the conjugate of the first one there, and I have to divide by itself. Okay, so that's the strategy when I see the square roots. Now when you multiply conjugates, remember first times first and last times last. So the square root of x plus 3 times the square root of x plus 3, well, that's just x plus 3. And negative 2 times positive 2, that's negative 4. Now for the denominator, I'm not even going to try. This is too much for me. I'm just going to write them next to each other. X minus 1 times that quantity. And if I played my cards the right way, then it shouldn't really matter that I'm not multiplying there. So x minus 1 quantity times square root of x plus 3. And then outside the radical, oh, let me just try that again. Square root of x plus 3 and plus 2 outside the radical. This is the limit. Don't forget to keep on writing this down. The limit as x approaches 1. So then let's see. I have like terms there, so this will turn into the limit as x approaches 1 of x minus 1 over x minus 1, see what just happened there? Times the square root of x plus 3 plus 2. So this will cancel out, and now we'll just have the limit as x approaches 1 of 1, because everything else canceled out, over the square root of x plus 3 and then plus 2 outside the parentheses or outside the radical. Now we can plug in, and when I plug in a 1, this will be 1 over square root of 1 plus 3, 4 plus 2. The square root of 4 is 2, so I'll have 1 over 2 plus 2. 4. My answer, 1/4. So now I think I want to try number 10. It's a one-sided limit. The limit as x approaches 0 from the left of the square root of negative x. And in order to figure this out, it helps to think about the graph of the square root of negative x. I'm not familiar with the graph of the square root of negative x, but I do know what the graph of the square root of x looks like. So square root of x, that looks something like this. And just thinking about it, then I remember that, well, this negative in front of the x, that's just a reflection. And because it's in front of the x, it's a reflection across the y-axis. So then this is what the graph looks like for square root of negative x, a reflection across the y-axis. So something like this. And what if the negative was outside the radical? Then it would be the negative square root of x, and then it would look something like this, square root of negative square root of x. But right now I'm just interested in the piece above, square root of negative x. That's the x-axis, that's the y-axis. And now I can answer this question. It's very simple. It's the limit as x approaches 0 from the left side. No wonder they said from the left, because when I look at this graph, you can only let x go to 0 from the left side. So take a guess. If I'm approaching x from the left side, y seems to get very close to, 0. And there isn't much to do there. So the lesson is, if you can think of a parent function and then do a transformation of the parent function, then try that, because the graph will never lie. Okay, I think I am getting very close to 15 minutes, which is all I can upload to YouTube at this moment. So I hope this helped. See you in class.